Did you know ESA is sending a mission to Jupiter? It is called JUICE, and for me it's the most stunning ESA mission ever. A European rocket flying a European probe equipped with mostly European instruments. But even NASA has an instrument on JUICE. JUICE is going to visit the icy moons of Jupiter, but even if it's freezing cold out there, it is the hottest candidate scientists could choose searching for extraterrestrial life in the solar system. I went to Toulouse in France to speak with the people building this probe and was also able to be up close with JUICE. Do you know why JUICE has the largest solar panels of any research probe ever? Why the main antenna for communication with the Earth is deliberately turned away from the Earth, and why the exploration of the icy moons has such a great relevance. We clarify all of this and much more today. I'm Mo, I'm a naval architect from Hamburg, Germany, and my channel Senkrechtstarter is the largest space channel in the German-speaking world. Since many of my video topics are not available in English, I have opened an English language secondary channel here, Senkrechtstarter Global. In case you're wondering what Senkrechtstarter means, it's the German word for vertical takeoff. The Jupiter Icy Moons Explorer called JUICE is an interplanetary spacecraft developed by ESA. The mission will study 3 of Jupiter's Galilean moons, Ganymede, Callisto and Europa. Galilean is the name of the 4 largest moons of Jupiter because of Galileo the Discoverer. Besides the 3 mentioned, Io is missing, but it's not an icy moon and so JUICE does not visit it. Sorry bro. Icy moons are so exciting because it is believed that there are large amounts of liquid water beneath their surfaces, making them potentially habitable environments. Never before has a mission managed by ESA been sent as far out as JUICE. Jupiter and its moons are really damn far out. Even if Jupiter is at its closest to Earth in its orbit, it is more than 10 times the distance from Earth to Mars. Yeah, you know what that means? It would take a very powerful rocket to reach the necessary speed for this journey. Currently there is only one rocket that can do it the direct way, the SLS. And in fact, NASA's counterpart to JUICE, the Europa Clipper, was originally intended to launch on the SLS. Okay, but if there's currently no rocket that can do this directly, how does JUICE do it with an Ariane 5? You probably already know, with swing-by maneuvers and gravity assists. If you're more interested in the topic of swing-bys and gravity assists and how the Voyager probes were able to leave the solar system with them, I made a German video on this topic. I'll link it to you under the video. Maybe I will translate it into English in the future. Briefly summarized, spacecraft can be accelerated or decelerated with clever flybys of planets or moons. In many cases, it is more favorable to take detours in order to be able to accomplish these maneuvers than to take the direct way. JUICE undertakes the full of 10 of these flybys for the outbound flight. Therefore, JUICE can be much larger and heavier than if Ariane 5 had to send the probe directly to Jupiter. In fact, Ariane 5 even sends JUICE in the wrong direction first, namely to Venus, in order to build up additional speed with it. Not only that, but JUICE also flies past Earth 2 more times after its visit to Venus to get extra momentum, then slingshots its way to Jupiter. On the arrival on Jupiter, JUICE uses the gravity of Jupiter to brake. After all, we want to get stuck in Jupiter's system instead of just doing a short flyby like the Voyager probes did. With this gravity assist, the JUICE spacecraft again saves fuel, which then benefits the mission's length. At the start of its journey, JUICE weighs more than 5 tons, of which more than 3 tons is the propellant. The fuel is then also the limiting factor when the mission has to end. Why even an electric alignment with flywheels needs thrusters even now and then, which then consumes fuel, I explained in my video about flywheels and control moment gyros, also linked below the video. But it is also recorded in German. Do you want me to translate it? Let me know in the comments. Gravity assists, cool stuff, but that will make the mission travel time much longer. JUICE is scheduled to arrive in the Jupiter system in 2031, after its launch now in April of 2023. Of course, this many maneuvers have the disadvantage that the flight plan becomes unbelievably complex, and if you screw up just one of these maneuvers, that's it for the unique Jupiter mission. Why JUICE still has an ace up in its sleeve, even with a single main engine, Cyril explains to you.
Yes, so effectively, these smaller thrusters that you can see there, these are 20 Newton thrusters.
A little bit more than this
A
one.
little bigger than the other ones, effectively. So these ones are used effectively for a number of reasons, but one of the reasons is to be able to make up for the main engine in case of failure. It is a very unlikely failure, but in case it would happen during a critical insertion maneuver, like at Jupiter, for example, we are able to complete the maneuver using these smaller thrusters. We have a pod of thrusters at each of the four corners of this lower face of the spacecraft, and we can use all of them all together in replacement of the main engine in case of failure to complete a maneuver, yes.
And will they use more propellant than the main engine, or is it like similar?
No, you are right. In case of failure, we are able to complete the maneuver with the thrusters, but there is a penalty. They will overconsume a bit the propellants. So there is a penalty that will impact the mission later on. We will have to reduce a few parts of the mission. But the good point is that we have a mission. Yeah. So it is robust to, again, a very unlikely failure of the main engine.
In addition to the 400 Newton main engine used for the large orbital maneuvers, JUICE has 8 20 Newton engines for smaller maneuvers and as a backup system. 12 10 Newton thrusters provide attitude control. The hypergolic propellant monomethylhydrazine and mixed nitrogen oxides as oxidizer is each housed in a 1600 liters titanium tank. Okay, now we have clarified how JUICE gets to Jupiter and to its icy moons, but how is it supplied there? As I said at the beginning, JUICE is powered by the largest solar panels ever installed on a research probe. The 10 panels are a full 85 square meters in size. That's about the size of our apartment here. They don't have to be that big because the ESA scientists secretly want to mine cryptocurrency on Jupiter, but because Jupiter is so damn far away and therefore much less sunlight per square meters reaches the probe than at the distance of the Earth. While here at the distance of Earth, the solar radiation burns an average of 1368 watts per square meter. At Jupiter, it is less than 50 watts per square meter in the worst case. And even these 50 watts still have to be converted into electricity by the solar cells with their efficiency. JUICE relies on gallium arsenide thin-film solar cells because of the low intensity of the sun and low temperature.
All spacecraft systems are electrically fed, let's say, with electricity coming from the solar panels, effectively. So they will be installed on these two faces. They will be 85 meters squares in total, so that's a very large solar array. For an interplanetary mission, this is the largest solar array we have ever built. But with such a surface at Jupiter, we will only generate 800 watts. It's not so much. So in fact, in designing the electrical concept of a spacecraft, we have really chased every watt that is lost in power converters, in cables, in under-efficiency of electronics design in order to really use to the maximum possible extent the electricity, the power generated from the solar panels for the benefit of the instruments. Of course, everything we do here is for the benefit of the instruments.
While great foresight and conservation of energy is required for transportation and instruments, JUICE's trajectory has kept the engineers sweating. On its way to Jupiter, as mentioned, JUICE will also enter the inner solar system to fly past Venus. This means, for example, that the solar panels must also function over the wide temperature range of plus 110 degrees Celsius to minus 230 degrees Celsius. Especially the proximity to the Sun at Venus was a real challenge for the temperature management. Unfortunately, it's very warm there, and since the instruments have a relatively narrow temperature range in which they feel comfortable, they have these MLIs, which then insulate the entire spacecraft and regulate the thermal balance a bit. That you don't give off too much heat, because everything you give off in heat, the solar arrays have to produce again as electricity for the heaters, and if you give off too little, then the thing overheats. To test the thermal management, JUICE went to the Netherlands to ESA's headquarters ESTEC for the first thermal vacuum test. The chamber walls were cooled down with liquid nitrogen to simulate the cold of space, but they also had a solar simulator to simulate the heat JUICE would experience near Venus. But JUICE is actually built for the exploration in the Jupiter environment. In order not to change the complete architecture of the probe for the relatively short time near Venus, the huge main antenna is used as a sunshade. The only side effect of this is that the antenna cannot be pointed at Earth at the same time to receive or transmit data. For this purpose, there is then a smaller directional antenna that can also be pointed at the Earth independently of the orientation of JUICE.
So this high-gain antenna that you can see there is effectively used during the first 4 or 5 years of the mission, not at all as an antenna, but as a big sun shield. In fact, this face of a spacecraft will constantly look at the sun during the inner cruise of a journey to Jupiter. It is a choice that we have made in order to not completely de-optimize the thermal concept of a spacecraft, which is of course primarily intended to work in a very cold environment. So in order to decouple at the most possible extent what is inside the spacecraft to the external flux coming from the sun around Venus, we choose to use this face, and in particular this antenna, as a sun shield effectively.
So, and the communications with Earth when you're going to point this to the sun is?
With a medium gain antenna, which you can see, this is the black dish that we can see on top of the spacecraft. This antenna has a dish which is smaller, but it does not matter because we are close to the Earth. So we do not need such a large antenna as where we are around Jupiter. We are closer to the Earth. And this antenna is steerable around 2 axes. So even with a spacecraft, this face of a spacecraft, constantly looking at the sun, we can still maintain the Earth in the field of view of that medium gain antenna.
But the small antenna is also interesting at Jupiter because most of the instruments are mounted at the bottom of JUICE. If these are pointed to the moons to do the measurements, the main antenna also does not point in the direction of the Earth. But why do you have such a big antenna at all if the small one does it too? The 2.5 meters parabolic antenna naturally allows a much higher data rate than the small antenna. One design criteria when designing JUICE was to enable a daily downlink of at least 1.4 gigabytes. That may not sound like much in today's world. For comparison, a raw material of an average Senkrechtstarter episode is about 30 gigabytes. However, the footage only goes over fiber and a few hundred kilometers, so Natalie can cut the episode. To get a sense of how difficult the transition to Jupiter is, the signal transit time from Jupiter to Earth can be up to 1 hour and 46 minutes. This, of course, is not only problematic for data transmission, but prevents any real-time control of the probe, requiring careful pre-planning and autonomous execution of operations by JUICE. There are so many aspects of JUICE that fascinates me. Which one has impressed you the most so far? Feel free to write me below the video. Now JUICE has to get off the Earth. Like the James Webb launch, the launch of JUICE will use the European Ariane 5. For many people, the James Webb launch has been the most important Ariane 5 mission ever. Maybe the most important rocket launch for Europe ever. But should everything go smoothly with JUICE, Ariane 5 would also make itself immortal with this launch. JUICE will certainly change our understanding of Jupiter's icy moons. I spoke with the Science and Earth Observation Chief at Airbus, and he can imagine that a subsequent mission could one day bring samples back to Earth for analysis. Soil samples from Ganymede on Earth, the thought blows my mind. I would like to thank all the people involved in this great mission, especially Airbus and Toulouse, who gave me this unique insight and fulfilled my dream to stand next to a spaceship or a space probe flying to the moons of Jupiter. I will certainly tell my grandchildren about this. If the video inspired you, feel free to press the like and tell other people about it. And if you're new to Senkrechtstarter and don't want to miss more videos about spaceflight, rocket technology and the latest development in spaceflight, be sure to subscribe. Can't wait for the next big leaps out there, our personal Apollo moment. See you next time, always stay vertical, your Mo.